Hello friends, in the previous lecture we learnt that Newton's first law explains what happens to an object when no force acts on it. It either remains at rest or moves in a straight line with constant speed. Newton's second law answers the question of what happens to an object when one or more forces act on it. To learn this, we perform an experiment in which you push a block of mass m across a frictionless horizontal surface. When you exert some horizontal force F on the block, it moves with some acceleration a. If you apply a force twice as great on the same block, experimental results show that the acceleration of the block doubles. If you increase the applied force to 3F, the acceleration triples, and so on. From such observations, we conclude that the acceleration of an object is directly proportional to the force acting on it. We also know from the preceding lecture that the magnitude of the acceleration of an object is inversely proportional to its mass, that is, a is proportional to 1 upon m. From these proportionality statements, we find that a is directly proportional to F net upon m, or a is equal to k F net upon m. Here k is the proportionality constant. Since 1 Newton is defined as the net force required to accelerate 1 kg object at 1 meter per second square, k is equal to 1. So, the equation can be written as a is equal to F net upon m. This mathematical relationship is Newton's second law. In words, we can state it as: when viewed from an inertial reference frame, the acceleration of an object is directly proportional to the net force acting on it and inversely proportional to its mass. The equation for Newton's second law is usually written with F net on the left side, that is, F net is equal to m into a. This equation is simple, but we must use it cautiously. First, we must be certain about which body we are applying it to. Then F net must be the vector sum of all the forces that act on that body. Only forces that act on that body are to be included in the vector sum, not forces acting on other bodies that might be involved in the given situation. For example, if you are in a rugby scrum, the net force on you is the vector sum of all the pushes and pulls on your body. It does not include any push or pull on another player from you or from anyone else. Every time you work on a force problem, your first step is to clearly state the body to which you are applying Newton's law. Newton's second law also tells us that if the net force on a body is 0, the body's acceleration is 0. If the body is at rest, it stays at rest. If it is moving, it continues to move at constant velocity. In such cases, any forces on the body balance one another, and both the forces and the body are said to be in equilibrium. Commonly, the forces are also said to cancel one another, but the term cancel is tricky. It does not mean that the forces cease to exist. The forces still act on the body. Weight. The weight W of a body is the magnitude of the net force required to prevent the body from falling freely as measured by someone on the ground. For example, to keep a ball at rest, in your hand while you stand on the ground, you must provide an upward force to balance the gravitational force on the ball from earth. Suppose the magnitude of the gravitational force is 2 Newton, then the magnitude of your upward force must be 2 Newton, and thus the weight W of the ball is 2 Newton. The ball with a weight of 3 Newton would require a greater force from you, that is, a 3 Newton force will keep it at rest. In the second case, the gravitational force you must balance has a greater magnitude, that is 3 Newton. So, we say that this second ball is heavier than the first ball. Now, let us generalize the situation. Consider a body that has an acceleration of 0 relative to the ground, which we again assume to be an inertial frame. Two forces act on the body, a downward gravitational force and a balancing upward force of magnitude W. We can write Newton's second law for a vertical axis with the positive direction upward as F net y is equal to m a y. In our situation here, this becomes W minus F g is equal to m 0 or W is equal to F g. This equation tells us that the weight W of a body is equal to the magnitude F g of the gravitational force on the body. Substituting m g for F g, we get W is equal to m g. This equation relates a body's weight to its mass. To weigh a body means to measure its weight. One way to do this is to place the body on one of the pans of an equal arm balance and then place reference bodies whose masses are known on the other pan until we strike a balance, so that the gravitational force on two sides match. The masses on the pans then match and we know the mass of the body. If we know the value of g for the location of the balance, we can also find the weight of the body with weight equation, that is W is equal to mg. We can also weigh a body with a spring scale. The body stretches a spring moving a pointer along a scale that has been calibrated and marked in either mass or weight units. If the scale is marked in mass units, it is accurate only when the value of g is the same as where the scale was calibrated. The weight of a body must be measured when the body is not accelerating vertically relative to the ground. For example, you can measure your weight on a scale in your bathroom or on a fast train. However, if you repeat the measurement with the scale in an accelerating elevator, the reading differs from your weight because of acceleration. Such a measurement is called an apparent weight. We are to note that a body's weight is not its mass. Weight is the magnitude of force and is related to mass by weight equation. If you move a body to a point where the value of g is different, the body's mass and intrinsic property is not different, but the weight is. For example, the weight of a bowling ball having a mass of 7.2 kg is 71 Newton on earth, but only 12 Newton on the moon. The mass is same on earth and moon, but the free fall acceleration on the moon is only 1.6 meters per second square. The normal force. If you stand on a mattress, earth pulls you downward, but you remain stationary. The reason that the mattress, because it deforms downward due to you, pushes up on you. Similarly, if you stand on a floor, it deforms and pushes up on you. Even a seemingly rigid concrete floor does this. The push on you from the mattress or floor is a normal force. The name comes from the mathematical term normal, meaning perpendicular. The force on you from, say, the floor is perpendicular to the floor. Figure A shows an example. A block of mass m presses down on a table, deforming it somewhat because of the gravitational force Fg on the block. The table pushes up on the block with normal force Fn. The free body diagram for the block is given in figure B. Forces Fg and Fn are the only two forces on the block and they are both vertical. Thus, for the block we can write Newton's second law. For a positive upward y axis, F net y is equal to may as Fn minus Fg is equal to may. We know Fg is equal to mg, therefore, Fn minus mg is equal to may. Transposing, we get magnitude of the normal forces as Fn is equal to mg plus may and is again equal to m into g plus ay for any vertical acceleration ay of the table and block. If the table and block are not accelerating relative to the ground, ay is equal to 0 and we get Fn is equal to mg. Friction. If we either slide or attempt to slide a body over a surface, the motion is resisted by a bonding between the body and the surface. The resistance is considered to be a single force called either the frictional force or simply friction. This force is directed along the surface opposite the direction of the intended motion. Sometimes, to simplify a situation, friction is assumed to be negligible, that is, the surface is frictionless. Tension. When a cord or a rope is attached to a body and pulled firmly, the cord pulls on the body with a force T directed away from the body and along the cord. The force is often called a tension force because the cord is said to be in a state of tension or to be under tension, which means that it is being pulled firmly. The tension in the cord is the magnitude T of the force on the body. For example, if the force on the body from the cord has a magnitude T is equal to 50 Newton, the tension in the cord is 50 Newton. A cord is often said to be massless, meaning its mass is negligible compared to the body's mass and unstretchable. The cord then exists only as a connection between two bodies. It pulls on both bodies with the same force magnitude T, even if the bodies and the cord are accelerating and even if the cord runs around a massless, frictionless pulley as shown in figure B and C. Such a pulley has negligible mass compared to the bodies and negligible friction on its axle opposing its rotation. If the cord wraps halfway around a pulley as in figure C, the net force on the pulley from the cord has a magnitude 2T. Newton's third law. Two bodies are said to interact when they push or pull on each other, that is, when a force acts on each body due to the other body. For example, suppose you position a book P so it leans against a crate C. Then the book and the crate interact. There is a horizontal force FBC on the book from the crate or due to the crate, and a horizontal force FCB on the crate from the book or due to the book. Newton's third law now states that when two bodies interact, the forces on the bodies from each other are always equal in magnitude and opposite in direction. For the book and crate, we can write the law as a scalar form as FBC is equal to FCB, equal magnitudes, and in vector form we can write the law as FBC is equal to minus FCB, equal magnitudes and opposite directions. Here the minus sign means that the two forces are in opposite directions. We can call the forces between two interacting bodies a third law force pair. When any two bodies interact in any situation, a third law force pair is present. The book and crate are stationary, but the third law would still hold if they were moving and even if they were accelerating. As another example, let us find the third law force pairs involving the muskmelon in figure A, which lies on a table that stands on earth. The muskmelon interacts with the table and with earth. This time there are three bodies whose interactions we must sort out. Let's first focus on the forces acting on the muskmelon as shown in figure B. Force FCT is a normal force on the muskmelon from the table, and force FCE is the gravitational force on the muskmelon due to earth. But these forces are not a third law force pair because they are forces on a single body, the muskmelon, and not on two interacting bodies. To find a third law pair, we must focus not on the muskmelon but on the interaction between the muskmelon and one other body. In the muskmelon earth interaction as shown in figure C, earth pulls on the muskmelon with a gravitational force FCE and the muskmelon pulls on earth with a gravitational force FEC. These forces are a third law force pair because they are forces on two interacting bodies, the force on each due to other. Thus, by Newton's third law, FCE is equal to minus FEC. Next, in the muskmelon table interaction, the force on the muskmelon from table is FCT, and conversely the force on the table from the muskmelon is FTC as shown in figure D. These forces are also a third law force pair, and so FCT is equal to minus FTC. So friends, here we come to the end of our discussion in this lecture, and therefore we sum up. When viewed from an inertial reference frame, the acceleration of an object is directly proportional to the net force acting on it and inversely proportional to its mass. The weight W of a body is equal to the magnitude Fg of the gravitational force on the body. A normal force is the force on the body from a surface against which the body presses. The normal force is always perpendicular to the surface. A frictional force is the force on a body when the body slides or attempts to slide along a surface. The force is always parallel to the surface and directed so as to oppose the sliding. On a frictionless surface, the frictional force is negligible. When two bodies interact, the forces on the bodies from each other are always equal in magnitude and opposite in direction. So that is it for today. See you in the next lecture with more on Newtonian mechanics. Thank you very much.